Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of vectors, and this is mainly for a trigonometry course or a pre-calculus course, as long as you've had trig, because trig is going to be very useful in a video from now. So let's go ahead and in this video talk about the arithmetic of vectors and properties of vectors. They kind of glue together in a nice single video. It's kind of a leisurely walk through vector arithmetic. So let's see, algebraic sum of vectors and scalar multiplication. Now you have seen my video on the geometric approach to vectors, so you know when you add two vectors geometrically, it's tail to head addition, right? Or head to tail addition, however you want to say that. Some people say tail to head, some people say head to tail. Doesn't really matter. Fact is, you glue the two vectors together, and then the result, or the summation, is the vector that starts at the initial point of the first vector and ends at the terminal point of the second vector. Okay. Geometrically, that's what we did. Now, algebraically, the sum of two vectors, u and v in this case is what we're calling them, is just the sum of their components, the vector containing the sum of their components. So if u, the vector u is u1 comma u2, and the vector v is v1 comma v2, we're going to define the sum of the vectors u and v to be u1 plus v1 and u2 plus v2. That's the second component, u2 plus v2. And likewise, we'll define scalar multiplication, or the scalar product, so a product of a number like 5 and a vector, to be each of the components of the vector multiplied by that number. Notice it is not me saying, oh, I'm going to take C and distribute it to one of them. It's not like that. The scalar attaches to each of the components of the vector. It sizes or scales each of those components accordingly. So if I multiplied this vector v by 5, it would scale the horizontal component by 5 and scale the vertical component by a factor of 5 as well. That's important to note. Here are our friendly vectors we've been dealing with for the past few videos. Let v equal negative 3 comma 1 and u equal the vector 5, 5. Compute 3u minus 6v. Now, according to that definition, 3 times the vector u minus 6 times the vector v is the same thing as 3 times the vector u is 5, 5, minus 6 times the vector negative 3 comma 1. Now, scalar multiplication, I'll just take this 3 and scale up each of the components of this vector by that factor. So my new vector here is 15 comma 15. And I'll go ahead and take this negative 6 and scale each of the components by that negative 6. So I have plus the new vector 18 comma negative 6. And now we know how to add two vectors. You just take their like components and add them. So this will be 15 plus 18 comma 15 minus 6. And the final vector that represents the summation will be 33. Oh, I don't know what just happened there. Will be 33 comma 9. I don't want to draw that because obviously that is pretty large, a pretty large vector, over 33 units and up 9 units, but that's the algebraic sum of those two vectors. So 3u minus 6v. Now let's talk about some very important properties of vectors. Now, a lot of people would see this list and be intimidated initially because they're not really paying attention to what's going on here. But these are what I call well, not just what I call, what most mathematicians will call the axioms. So the axioms that build all the mathematics around you from arithmetic on up, most of them are represented here. Not all of them, but most of them. So for example, the first axiom is that addition is commutative. In other words, normally with arithmetic, you'd say a plus b is b plus a. Well, vectors also have that property. A vector u plus a vector v is the same thing as the vector v plus the vector u. So our natural thinking about how addition works as far as commutative properties, it works fine with addition of vectors. So nothing is different there. Same thing with the associative property. That's an axiom in arithmetic. It's part of how we build all of mathematics. There's only 10 of these axioms that builds everything you do in mathematics. So that's what math is. It's a game with 10 rules. That's all it is. It's just that you have to, as rules get built, they create sub-rules. And so anyway, but everything is built on those 10 axioms. So the second axiom is the associative property of addition, and it turns out that it works with vectors as well. The vector u plus the vector v plus the vector w, you could add v plus w first and then add u, or you could add u and v first and then add the vector w. The third one there, the additive identity, that is also an axiom. In arithmetic, a plus 0 is just a. In vector arithmetic, the vector u plus the 0 vector, which is a vector full of zeros, so it looks like this in 2 dimensions, is just going to return the original vector u. So that's the additive identity. Then we have the additive inverse. So the additive inverse in arithmetic is a number plus its opposite will always be 0. Well, the same thing with vectors. A vector plus its opposite will be the 0 vector. That's important to note. It's the 0 vector. The result is still a vector though. All right, let's see what we have here. Now, this is not one of the axioms that's from arithmetic, but it's very similar anyway. If you have the magnitude of a scalar times a vector, you could break those apart, look at the magnitude of the scalar, the absolute value of it, and multiply that by the magnitude of the original vector. So that's new. That's not, it still works actually just like our old properties. We have one with absolute values. The absolute value of a times b is the same thing as the absolute value of a times the absolute value of b. It is true still for in arithmetic for real numbers, but here's the vector version of it. Then we have the distributive properties, which are the same distributive properties that you'd have with arithmetic. In arithmetic, c times a plus b is ca plus cb. Well, same thing with vectors. C times the summation of the vectors u and v is c times the vector u plus c times the vector v. Likewise, c plus d times the vector u is c times the vector u plus d times the vector u. So those are the distributive properties. They exist from arithmetic. Then you have the associative property of scalar multiplication. So if you have the product of 2 scalars, and then you want to multiply a vector, it'd be the same thing as taking the second scalar and multiplying it by the vector and then multiplying by the first scalar. Or you could commute things around and say, no, I'm going to multiply the first scalar against the vector and then the second scalar. It's just saying you can multiply in any order as long as it's just a single vector times scalars. We do not right now have any rules about multiplying vectors. So, and in fact, in the courses that I'm teaching, we do not have rules about multiplying vectors, okay? Then we have the multiplicative identity. The number 1 times a vector u is just the vector u. And then we have the multiplicative 0, right? Or nullification properties. The number 0 times the vector u is always going to be the vector 0. Let's see. And then finally, a constant times the 0 vector is always a 0 vector. Most of these should be somewhat natural for you to understand, but if they're not, spend some time thinking about why these are true. You end up proving a lot of properties around these when you get to linear algebra. Linear algebra is such a neat course, but it's often very difficult for people because it's so low level. It's so simple. Your brain is operating on high octane at that point. And when you get into linear algebra, it's like it's a weird twist to your imagination. All right, so let's go ahead and finish out this video with some arithmetic. We're going to use our same two vectors we've been using all along, just compute each of these. So let's compute 2 times u. Well, that's going to be pretty easy. That's 2 times 5, the vector 5, 5, which we know is going to be 10, 10. Okay. Negative 1/4 times v. Well, that's a negative 1/4 times the vector negative 3, comma 1. Or in other words, 3/4, comma negative 1/4. So both of those should not be too terrible. All right, let's take a look at that magnitude of 2u. Now we've already computed 2u. It's right up here. So the magnitude of 2u is going to be the square root of the first component squared plus the second component squared. That is going to be 100 plus 100 or square root of 200, which is 10 root 2. 10 times the square root of 2. Same thing, let's do the magnitude of 1/2 v. Would have been nice if I had done the magnitude of negative 1/4 v, but I didn't. So let's just go ahead and do this. It's the magnitude of 1/2 times the vector v. So we have to compute that first. That's the magnitude of negative 3/2, comma 1/2. And we know that is going to be the square root of the sum of the squares of its components. So the square root of a negative 3/2 being squared and a 1/2 being squared, which is going to be the square root of 9/4 plus 1/4, or 10 over 4. And that is just going to be 1/2 root 10. There's not much else you could do with that. That's the size of that vector. That's also, by the way, what you should always think about when you see a magnitude. You should say, oh, that's the size of that vector. U plus v, I think we've already done, well, no, maybe we haven't. U plus v. Well, this is going to be a negative 3, comma 1 plus 5, comma 5. That should make sense. You add like components, so it's going to be negative 3 plus 5, or 2, and 1 plus 5, or 6. And then the next question is saying, well, what's the size of that vector, right? So that'll be the square root of the sum of the squares of its components, so 4 plus 36, or square root of 40. Should really reduce that radical though. So that's going to be 2 root 10. That's the size of that vector. The second, or part G there, is saying, well, what about the magnitude of u minus v? Now, G and H are really important questions here. Let's see. The magnitude of u minus v. U was a negative 3, comma 1, minus v was 5, comma 5. Now, we didn't really define subtraction, but subtraction is basically saying negative 3 minus 5 and 1 minus 5. So I hope you guys are at a level you could totally understand that. Negative 3 minus 5, we get a negative 8. 1 minus 5, we get a negative 4. And we want to know the magnitude of that difference. That is going to be the square root of 64 plus 16, or the square root of 80. And let's see, that's, I think that's 16. Nope, that's not. Yeah, it is. 16 times 5, and square root of 16 is 4. So that's 4 root 5. Now, why I say this is an important question is because it turns out that magnitudes don't play well with addition or subtraction. The magnitude of u, which we've computed earlier, somewhere up here. Oh, I guess we didn't. Oh, well. The magnitude, oh, we did on a different page. The magnitude of u, when we computed it previously, is 5 root 2 minus the magnitude of v is the square root of 10. Notice you cannot really add those two radicals up. And notice also, this is not equal to the magnitude of u minus v. That's critical to note. So With addition and subtraction, those are really terrible operations, so you can't really break things across addition and subtraction. Specifically, you cannot break magnitudes across addition and subtraction. So the magnitude of u minus the magnitude of v is not the magnitude of u minus v. And that does it for this video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.